Good afternoon. It's not muted. I just did. Okay. Can you hear me though? Now it works, right? Okay. So one thing is the homework. I moved the due date. I think you're happy, right? I moved the due date for you. You should be happy. Wait, that's the wrong one. I want this one. So we have only a couple topics left, and then we might teach you how to play card tricks. Okay, so last time we learned about expected value, right? That it is nothing but the mean, and we learned that there's one very important properties of expected value, which is called linearity of expectation, right? So you learn this guy, e of x plus y is e x plus e y. Okay, and I made a note that the reason that this thing is so powerful, this does not require x and y to be independent. The reason that this thing is so generic, so versatile, is because back to the HD camera. You know, the HD camera that you think I have is actually my iPhone. Actually, my iPhone. Last time was so bad, right? Let me get rid of that one. iPhone 4. I used to have iPhone 4, but not anymore. Okay, so this time, so we learned something about the sum, right? So let me ask you something simple. The property of expected value. You learned the most important one last time. Let me ask you something simple. So for example, let's say let's get it a little bit more physical. Let's say D1 is the face of the dice. What if I want expected value of, I don't know, pi 3.14 something multiplied by D1? Any guess? You can prove it in 2 lines, but any guess? Any guess? That what that means that take the face of the dice multiplied by pi and then take the average. Any guess? Good. So you would expect, right, that it's going to be pi times e of d1, right? So now you know that you can pull the constant. Yeah, it's very important. This thing is a constant, right? Pi is not a variable. It's a number. It's like number 3. Okay. So let's do this. Let's do something interesting. Okay. Let's do something interesting. So for example, what about if you have 2 dice, D1 and D2, 2 dice, okay? Now you're gonna multiply them together. Notice how this is different from last time, right? Last time, what you were doing is you multiplying a constant, but this time you are multiplying the 2 dice together, D1 multiplied by D2. What do you think? Any guess? Any guess? Any guess? You have 2 dice, you roll them. So you would expect something like this, right? You expect something like this. If this happens, then that means you learn too much physics and you hope that the formula looks like, but actually it's a no. Actually it's a no. This thing actually a no. This thing is only if they're independent, which we're gonna show. Only if D1 and D2 are independent. Okay, let me show you. Okay, let's prove exactly this property. Okay, let's prove this. Okay. Let's prove this property. So we know to find this expected value of D1 times D2, right? The thing that you need to calculate, you see my full screen, right? Because it's right on top of a whole bunch of things. Expected value of D1 times D2, right? This is what we want to calculate. Okay, it is the mean, and then we know there are many ways to group the mean, right? Let's group it this way: the sum over K, right, of K multiplied by probability that D1 times D2 is equal to K. That's how you find the average, right? So for example, you multiply 5 by probability that the product is 5 equal to 5. You multiply 4 plus 4 multiplied by the fact that the probability that the product is equal to 4 and so on. Then you sum it up. We did that last time. Okay, when we sum up the expected value. Okay, which is exactly this guy, right? Which is exactly this guy, which I'm going to show you is for I and sum over J. Okay, and I just call K equals I and J. So this is what happened. I times J multiplied by the probability that D1 is equal to I and D2 is equal to J. Right? So I just call K I times J. That's all. Right? And then all you need to do is that you just need to sum over all the possible product multiplied by the associated probabilities. Any questions so far though? Any questions so far? So far, we haven't assumed independence, right? So far, we haven't assumed independence. Someone with me so far though? The symbol may look confusing, but you can ask. Any questions so far? Where did the second one come from? It comes from the fact that you can sum it over all the possible product, right? All the possible product multiplied by the associated probabilities. So essentially K is I times J. I did not assume, I define. I define to be I times J. This thing is, these two are similar, but I can actually just write this guy because it's like straight from the definition. But this one might make you more confused or less confused depending on how you look at it. But are you convinced though that this guy, expected value of D1 times D2, right? If D1 is I, D2 is J, the associated weight is this guy. Are we good? So for example, let's say that the term that is 12, let's say K is 12. Let's say K is 12. You want a product to be 12, right? There are many ways to do it, right? There is 3 times 4, right? So there's going to be a term that's 3 times 4, probability that D1 is equal to 3 and D2 is equal to 4, right? That's one thing. Plus 4 times 3, P that D1 is 4, D2 is 3, right? Plus 2 times 6, P probability that you get 2 and 6, right? And then there's a 6 times 2 probability that you get 6 and 2, and so on. Everyone got the idea, right? Now what, are you convinced that this is the expected value? Okay. So think about this, all these are 12, right? And these are, if you add them up, right? All the 12, all these 12, 12, 12, gonna be factor out, and all these guys, right? They're gonna add up to the probability of getting 12, doesn't matter how. That sounds good? Okay, so far, up until here, we haven't used the fact, right? We haven't used the fact that D1 and D2 are independent at all, right? So far we haven't used it. Okay, so if I know, okay, let me say, if I know that D1 and D2 are independent, okay, if I know that D1 and D2 are independent, what do I know? What do I know? So especially about this term, what do I know? P of A and B, what do I know? If they're independent, what do I know? Very good. If they're independent, so this guy gonna become P of D1 equals to I multiplied by P of D2 is equal to J. Okay. That's good. Right. So let's do this. So this thing gonna become sum of I, sum of J and then I times j, and then probability that d1 is equal to I multiplied by probability that d2 is equal to j. And again, this step requires independence. This is not true. We're going to show counterexample that this is not true if they are not independent. Okay, everyone is good? Right, everyone is good? Which you learned by now, right? Let me get rid of this. Let me get rid of this. I'm going to move j to here. It doesn't matter, right? I'm going to move j to here. Okay, so the first parentheses are all the functions of I, and all the second parenthesis is the function of j. You learned it when we did the double sum, right? When we did the double sum, that this guy is going to be sum over I of I times probability that d1 is equal to I. I think you have seen it before. Multiplied by sum over j of j multiplied by probability that d2 is equal to j. Am I missing so far though? Are you with me so far? This is like a leap of faith, but you have seen it before. You're not with me. You have seen this guy before. If you remember sum over I and sum over j of fi g of j. You have seen this before, right? That this guy is going to be sum of f, sum of g, multiply them together. You have seen this before because I taught you myself. You have seen this before. Okay. Does that sound good? Right? And before I repeat it again, let me ask you, does this guy look familiar though? What is it? Does that guy look familiar though? Very good. It's the expected value of D1, right? So let me move it up top. So this guy is E of D1 multiplied by E of D2. And we have proved what we need to do. Right? We have proved what we need to do. So this is true only if they're independent. And like I said, independent is a strong condition, a really, really strong condition. But typically we assume that, otherwise we cannot do math. Otherwise the math is too complicated. Okay, so far so good. Any questions so far though? Any questions so far? So we have shown that if D1 and D2 are independent, okay, then the product of the random variable, the expected value of the product is the product of the expected values if they are independent. If this is a really big if, let me make it a really big if. This is a big if. Okay. Unlike the sum, right? The sum, you can use it any way you like. But this is interesting. So for example, it helps you calculate the following number. I actually put this in an interview question, but no one answered it in the way that I want them to do, but it doesn't matter. So for example, let's go back to the question of two dice. You roll them up. You take the product. Okay, two dice, you roll them up, you take the product. Then I ask you, what is expected value of D1 and D2? Okay, D1 times D2. So, and then I tell you that, okay, they are independent. So that means I roll them without cheating each other. Okay, they're independent. What do you know? What is it equal to? Can anyone tell me? If D1 and D2 are independent, good. So it's going to be E of D1 multiplied by E of D2, which is, what is E of D1? What is the expected value of the dice, of a dice? 3.5, right? So this guy is going to be 3.5 square. Okay, very simple. This guy is going to be 3.5 square. But What if they are not independent? Okay, what if they're not independent? Any questions so far though? Any questions so far about this? If they're independent, then you can just do this. Just multiply 3.5 together, whatever the number you get. Okay, y 3.5, 1 plus 2 plus 3 plus 4 plus 5 plus 6. And each one of them has 1/6 probability. Please. Okay, now if the two dice are not independent, so for example, D1, right? D1 and D2 are always the same, right? So if D1 and D2 are always the same, so that means you can only get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6, right? We showed you last time, right? If you add them up, then it doesn't matter how you cheat the dice as long as you didn't screw up the probabilities. Okay? D1 and D2 looks like this. So that means if you try to calculate the expected value of D1 times D2, okay, then you cannot use this anymore, right? This is like a no, because they're not independent anymore. So you just need to resort to like brute force, right? So you just calculate all the possible values, right? You know that there's a way for you to get 1, 1, right? That's a 1 square multiplied by 1 over what, 6, right? Or 36. Actually 1 over 6 plus 2 square multiplied by 1/6 plus 3 square multiplied by 1/6 plus 4 square multiplied by 1/6 plus 5 square multiplied by 1/6 plus 6 square multiplied by 1/6, which turns out to be, I don't know, what's the number? 1, 4, 9, that's 14, 30, 66, 71, no, 91, which is not that number. Which is not that number. What is it? 15, 106. Yes, equals to 15, 1 over 6, and I need to fix my lecture note. Okay, which is not 3.5 times 3.5, that's like 12. Yes, so remember the intuition for independence means that uh, the information about one thing doesn't tell you anything, doesn't change your information about the other thing, right? So if D1 tells exactly what D2 is, that's like the exact opposite of being independent. Okay, so far so good. So we learned this. This is not bad, right? Okay, we learn how to do the property of the product. Okay, how about the ratio? I said that independence means that information about one event doesn't tell you anything about the other event. Okay, in this case where D1 tells you exactly what happens with D2, right? If you know D1 is 1, you know exactly what D2 is. That is the exact opposite of being independent. Okay, there are things in between as well, not just either completely independent or like completely dependent on each other. Okay, so let's do the expected value of ratio. Okay, expected value of ratio. Okay, let me guess. Let me take a guess. What do you think this guy is? Any guess? Expected value of the ratio. Any guess? What's so tempting to do? What's so tempting to do? Good. Very good. That means you learn too much physics. All the formula in physics look so nice. But no, they are not equal. Let me show you. Let me show you. They are not equal. They are not equal. Okay. So for example, let's consider a random variable R. Okay. I just want to show you now. I'm going to show you example, which you kind of scam people with this example for sure. R has two things. One with probability a half, and -1 with probability a half as well. Okay. So let me ask you, what is E of R? A simple question. Tell me. Expected value of R, what is it? It can go 1 with a half, and it can go -1 with probability a half. So what is the expected value of R? 0. Good. That means the right hand side is 1/0. Right? That means the right hand side is 1/0. The left hand side, however, you can calculate it, right? The left hand side, 1/R, you know it's the exact random variable, right? Because it's 1/1 with probability a half. And this thing is probability a half. Right? 1/R. Give you exactly the same distribution, right? Because 1/1 is 1, 1/-1 is -1. The probability are the same. And that means expected value of 1/R is how much? You can tell me. Expected value of 1/R? How much? How much? 1/R looks like this. Not a half, it's still 0. Right? It's a half times 1. That's what we do, right? You multiply a half times 1 plus a half times -1. So that's still 0, which is not the same, right? I want to point out that expected value of the ratio, you cannot just do this. You can't just do this. You can do it with the product. Okay. Any questions so far though? Any questions so far? This may look trivial now, right? But trust me, let me show you something not so trivial. Not so trivial. Let me do this. Do people still play Angry Bird though? Do people still play Angry Bird? Come on, paste, please. Okay, I'm gonna cancel it. And I'm gonna paste it again. And no, that's a graph from yesterday. Wait a second. 1, 2, 3. Okay, I'm give it 3 seconds. What? There, that's what I need, not this guy. This one is from coverage problem. Okay, so let's do this. Can I go back a bit? Do I still need to go back, Keith? Oh no? So let's look at this table. Look at this table. This sounds like a very good thing. Okay. So for example, this is a very smart thing to do, right? So for example, if you want the last thing, so if you want to know whether Samsung phone or Apple phone is better, right? Better means faster, right? You're not going to compare the raw frequencies. That's a silly thing to do because if you learn system skill before, you know, right? There's a time that if the CPU needs to fetch the memory and so on. That's why M1 is so fast, because the RAM is right next to the CPU. It doesn't need to go to the motherboard and go to the RAM. That's why M1 is so fast. Even though the clock speed is not that impressive, but it's really fast because the memory fetching is so fast. Okay, so comparing CPU is so hard. One way people can do, okay, right? One thing people can do, right, is what? One thing people can do is the following, right? To take the time, the Samsung, how long it takes to open Angry Bird? Okay, how long it takes for iPhone to open Angry Bird? 150 seconds and 120 seconds. So that means we can take the ratio, right? We can take the ratio. We can take the ratio. Sounds about right. 150 over 120, that's 1.25, right? So that's clear. If it's more than one, that means Samsung is slower. If it's less than one, then it means the other way. Are we good? Okay, so we can take the ratio. We can do the same thing for Line. Line gets much slower to open these days. I don't know what they are doing. Okay, so that's good. So you look at the time, look at the time, look at the time. Then you take the ratio. Then you take the ratio. Let me do this. Let me censor this for now. You're gonna see it later. Okay. I'm gonna display it later. Let me censor it for now. So for example, you take the average for some of the application, right? For some of the application, Apple's gonna be faster, right? Less than one means faster. Less than one means faster. This means Apple is slower. Okay, that sounds good, right? Then what we do, right? What we're gonna do is we're gonna take all these ratio, but we have 4 applications. What do you do? We have 4 applications. What do you do to get the final number? I think it's very natural for you to do, right? To take the average, then it says, okay, the average is 1.2, right? You sum it up and then divide by the number, right? Add of them all up and then divide by the number. You get 1.2. So that means, so you can say that Apple, on average, whatever that means, on average is 20% slower. Is that one good? That one good? You can check the number though. You can check the number, the ratio and the average. You can check the number. Everyone good, right? Now, let's do it the other way. Okay, everyone understand my argument, right? The fact that I say that Apple is slower because the average is 1.2, right? And I say that 1 is slow. Are we good? Then we can do the reverse. The reverse says the following, that okay, I'm going to take the reverse, right? You can check, right? 101.8 is 1.25, 101.5 is 0.67, and so on. And then you take the average. You take the average and you come out to 1.1. And then you found out, oh, wait, but even though Apple is on average 20% slower, Samsung is also 10% slower than Apple. It's 10% slower than Apple. You can check the math though, right? That's exactly what you do. That's exactly what you just did. You take the ratio, you take the average. And this is how marketing scam people, because people don't know how to interpret this number. Right? Is that good though? Everyone happy with what you're saying, right? You don't know why yet, but you kind of agree with me that if you do this, if Apple is 20% slower and then Samsung is also 10% slower than Apple. Right. So the first method, what we did is we take Apple, divide by Samsung, and then we take the average. Right. And the other one is, okay, we take the Samsung over Apple, and then we take the average. We found out that both of them is more than 1. Yeah, we found out that both of them is more than 1, so we don't know what's going on, right? What's going on though? Anyone know what's going on? The number is correct, trust me. The number is correct. I put it on Excel, and unless Excel has a bug. Anyone know what's going on? We have a bug. What's going on? Anyone know what exactly are we doing though? What exactly are we doing? We are taking the expectation of ratio, right? This is something to be careful of. This is close to the ally problem. This is close. It's actually related, but not quite. So what we are doing here is expected value of Samsung over Apple, right? which is not expected value of Samsung over expected value of Apple. That also means if this guy is more than one, that it doesn't mean this conclusion is kind of wrong, that Samsung on average is 20% lower than Apple. So that also means that if this guy is greater than equal to one, that doesn't mean expected value of Samsung is greater than expected value of Apple. Okay, right? We did this before. These two are not equal, so you cannot make this jump to conclusion, right? You would jump to that kind of conclusion. We would say that okay, Samsung is slower than Apple and whatnot, but no, but don't, because you are based your conclusion on expected value of the ratio, which doesn't have a nice interpretation. Trust me, this thing happens more often than you think. So for example, you can take the COVID vaccine, for example. If you take the average of the ratio, then you need to be careful what you're doing, right? So for example, let's say you have คุณหมอยง Dr. Yong favorite Sinovac and AstraZeneca and Pfizer and Moderna, which I don't know, some of you get it already, some of you don't. You guys probably have Astra from Mahidol, right? Right, and then I say that this guy is 60% effective. Astra, I think it's 70%, and that guy is 80, right? Moderna is also about 80. This number like actually doesn't mean much. And this number actually doesn't mean much. Maybe, I don't know. Don't use my medical advice. And then you say, oh, on average, how effective is the vaccine? Once you average this number, then you're screwed. Once you average this number, you're sort of screwed. But the number, trust me, don't trust it. Don't trust it too much. It depends on the composition of variance. It depends on a whole bunch of other things. Okay, not medical advice. Good. Don't. So when you're my student, don't take the average of the ratio. Or if you want to screw people up, then you take the average of ratio and then fool them, because someone gonna trust you on this number anyway. Okay. Any questions so far though? Any questions so far? Any questions so far? So ES and A are not, even if they are independent, it doesn't help. It doesn't help. Right? So for example, number one and R are independent by definition. You can actually go to the definition and they are independent. Okay. Don't take the average of the ratio. You're gonna get something funny. Now let me ask you some more intuition. So how do you compare them? Whether Samsung or Apple is better? It's more like a religion question, right? How do you compare? Given this table, how if you were to compare it in any way, how would you compare them? You know by now, right? Average of the ratio. This is like a terrible idea. That is a terrible idea. How would you compare them? How would you compare them? What's a fairer metric? Okay, this is a startup time, by the way. How would you compare them? Anyone? Right? So when you want to compare something, this is what you're going to learn in machine learning as well. Not the difference, right? You want to compare the actual thing that have actual impact on your life, right? So for example, it kind of depends. If you use your phone to play Angry Bird all day, you don't really care about live Facebook or Skype, right? Oh, Skype doesn't exist anymore anyway. You don't care about this guy. Then you compare, like if you open 10 times on Angry Bird, how long will it take you? Right? Oh, I know why they doesn't exist anymore, because look at the number. Look at the number compared to these people. Okay, so Skype actually exists in Microsoft Teams, by the way. Microsoft Teams still use Skype, but you don't know it. Okay, so the way you do it, then you count how many times you open Facebook in a day, you open Line in a day, and then you calculate the total time you would have wasted if you use Apple or Samsung, and then you compare those numbers. Then that works. Okay. So I want you to get some intuition as well. Don't do this. This is like bad, misleading. But if you want to mislead people, this is what you do. You want to mislead people, this is what you do. But don't. Okay. So any questions so far though? If not, we're gonna take 10 minutes break and we're gonna come back and learn something about variance, which is what I want to teach you today. Today is 1450. Okay, come back 1450. Wait, Justin, I thought Mahidol provide vaccine to every single one of you. If you choose to take it, they don't force you. We cannot force you. Seriously. If you're under, then you might get Pfizer instead if you're underage. I think what you should do, did you contact a student association? They're going to help you. Someone going to help you at SA, student association. You should line, send them a message. Guys, Sinovac is not that bad. It's not that bad. The thing that happened, this is not medical advice, but that's a disclaimer. Sinovac is not that bad, guys. The thing that happens with the Sinovac number is because by the time Sinovac is out for market, what happens in China is that all the all the variants or all the COVID is gone from China, so they don't have anywhere to test. So once they've developed it, they go and test it on Chile or something, right? And Chile has another variant which they are not designed to do. So like I said, it depends on the variants. But my prediction is that you're gonna need like Pfizer version 2 and Moderna version 2 anyway. I sometimes teach physics 1 and intermediate mechanics. The best place to learn calculus. The best place to learn calculus is to learn with mechanics. That's actually how they come up with calculus. I don't know, but Ajahn Vitul and Ajahn Thane teach it. They are really good teacher as well. People love them. Yes, they're from Mahidol though, so they are not technically part-time because I am actually Mahidol employee. But you know, I'm not even their employee, that I am their contract worker. That's actually the official word. They call all the Ajahn the contract worker. Yes, but the one who actually pay me is my name is under MU. Everyone's name is under MU. MUIC is like a department. It's like when you have a company and then you have an office of accounting. So MUIC is like office of accounting. Yeah. So Ajahn are contract workers. We are not under labor law as well. So that means if they fire us, we don't get compensation. We don't. A lot of the law doesn't apply to Ajahn. I don't know who made it, but it's written specifically that that labor law doesn't apply to Ajahn. So that means all the benefit from labor law, we are not protected under labor law. Oh, if you want to discuss politics about teaching, I can tell you, right? Think about this. Think about this. Think about this. You guys, when you graduate, you are at even at my company, I pay fresh graduate more than my salary right now. So the salary for Ajahn is not that much. So we do it for for the memes, right? And that's why it's so hard to find a good CS program, but you guys are in good hands because all the good Ajahns, they can go to industry and get paid like 10 times the amount. So it's so hard to find good Ajahns because our salary is also based on it's also compared with other fields which is not much needed by the industry. So for example, in like tourism business and so on, if they don't be an Ajahn, they don't get paid that much. But for us, if we just leave and then we go somewhere, then we get paid like 10, 20 times the amount. So for example, Ajahn Kanat, he take like a whole bunch of division just to teach you guys, so be nice to him. He would have earned like so much more money if he doesn't teach you guys. So be really nice to him. Don't piss him off. It's a side hustle that takes so much time. Okay, so be nice to him. You guys are really lucky having Ajahn Sansan and Ajahn cannot teach you guys. Don't piss him off. Okay, so let's get back to our thing, the risk. Let's talk about risk. How about risk? Okay, I'm gonna ask you about the risk without having defined it. Okay, without defining it to you at all, but I'm gonna use your intuition. Okay, so for example, if I ask you for a game, okay, this game is tossing a coin, head or tail. The game called head or tail, like what we did last time, except I'm not scamming Justin anymore. This head or tail is fair. There is probably a half of you earning 1 baht and probably a half of you earning 1 baht. Okay, that's game A. Let's call that game A. Right, you get paid a bunch of money for risk management. Risk management is actually to do math. Unless you're like bullshitting your way through, that might work too. Okay, that's a game B. It's also probably a half of getting one, but not 1 baht, but 1 Bitcoin. So that's a million baht. I don't know how much is it today, 2 million, 1.5 million. I don't know. Let's call that 1.5 million. You can gonna play head or tail, but it's 1 Bitcoin. Let's say it's 1.5 million. I don't know how much it is today. Let me ask you, which one is more risky? Which one is more risky? The Bitcoin one, right? The Bitcoin one is way more risky. Why did you say that? Why would you say that? If you think about it, then Ajahn, that's easy. Just compare the mean. If you look at this, expected value of your payout from A, that's 0, right? We calculated before. Expected payout for B, that's also exactly 0. So well, but on average, you're gonna get 0. But why do you say? So yes, so the change, so that is something that quantify the risk, right? That has to do with like all the, that has to do with how much you lose each game, not the average. Okay, so we're going to find that number. Okay, we're going to find this number. This number is called variance. If you learned that before, if you do probability, you actually want to work more on variance because it's so nice to calculate. You don't need to square root everywhere. Okay, the variance, we're going to define it with the following. And I want to make sure you think about it, that it matches your intuition when you say that the 1 Bitcoin is much riskier than 1 baht game. Okay, so I say the following. The symbol gonna look like crazy. variance of R, what did I use? Variance of R is expected value of R minus expected value of R square. Right? Okay, so let's do this. Let's do this. Okay, I want you to think about how this thing match your intuition of what I drew on the last page. Okay. So what this guy is asking is the following. You have the outcome, right? Let's look at this is the outcome. Okay, there is game A. Oops, sorry. There's game A over here, 1 bar. And there's game B over here. There's a B over here. Right? You say that B is riskier because on average, it's further away from the zero, from the mean, right? So we say that B is riskier since it's further, is on average further away from the mean. Okay, so if you think about it, that complicated looking expression is just the distance of what you can get from the mean. Does someone get? Right? Okay. And then you ask what is the average of that distance, but then you're gonna ask Ajahn, why you bother to square, right? I think a lot of people are gonna ask that. Okay, let's do exactly what you need. Let's pretend we don't square it. Let's pretend you don't square it. What's gonna happen though? So let's say if we don't square it, this is what we got, right? Expected value of what we got minus the average. What do you think? What would you get if you calculate this? You calculate this. What you get? Just big. What would you get? Any guess? So what that means that okay. So let's calculate it together. Let's calculate it together. So for example, this thing is plus 1 Bitcoin, right? And this thing is going to be minus 1 Bitcoin because the average is 0, right? If you add them up, what's going to happen? Zero, right? It's going to be 0. This guy is guaranteed to be 0. By definition, you can use linearity expectation, right? So that guy becomes expected value of R minus expected value of R. Right? Expected value of R, that's a number. That's a number, right? Expected value of 5 is 5. If it rolls up 5 every time. So this is going to be E of R minus E of R, which is guaranteed to be 0. Okay, so the problem here is that if you don't square, then the thing that is on the right of the mean and the thing that's on the left of the mean, they're going to cancel out. Right? They are going to cancel out, and then you're going to get 0 every time. And then I ask you what's the risk? 0. I ask you what's the risk for the other game, you say 0. That makes no sense, right? The reason we square it is to make sure that the left, the negative people and the positive people, they do not cancel each other. That's why we square them. Okay, so far so good. And that kind of match, right, with your intuition of what a risk mean. A risk mean like how far you are from the average on average. Okay, so this is how far you are from the average on average. Okay. Okay, so let's do some example. Let's do some example to make sure that you guys understand this. Okay, so for example, okay, so variance is what? A half and a half, and then there's a 1 and minus 1, right? Let's look at the game. Okay, so the variance of this guy is going to be expected value of R minus expected value of R, then square. Okay, and that becomes, because expected value of R, we can calculate it, right? This number, we can calculate it, and this thing I think is 0. So it becomes expected value of R minus 0 square, right? So what you do to find the expected value, you get all the outcome multiplied by the associated probabilities, right? So this guy is going to become 1 square multiplied by a half plus minus 1 square multiplied by a half, which is whatever number that is 1. Okay. So what it is saying that it is on average, you're going to be 1 square distance away from the average. Okay. Right. So let me write this down. On average, we are the square distance. Let's say the square distance is 1. Distance from average as well. Someone get? Good. Let's do another example to make sure that we actually understand this. Okay, let's do another example. What if there's another game? Another game. You have also probability a half, probability a half. Okay. What did I write there? On average, the square distance from the average is 1. Okay, so let's do another example where they don't average to 0. Let's do the example where you average to 2 and 1. Okay, so you have probability a half of getting 2 baht and probability a half of getting 1 baht. You have probability a half of getting 2 baht and probability a half of getting 1 baht. Maybe it is because the pen is too big, but I like it already. Okay. So to calculate the variance of, let's say this game B, variance of B, right? Variance of B is going to be expected value of B minus expected value of B square. Okay. So the first thing that we need to find, let's make it 3 baht. Sorry, let's make it 3 baht. So at least I have some sort of integer to work with. Let's make it 3 baht. So now the average, right? Expected value of B is going to be 3 times 1/2 plus 1 times 1/2. It's going to be 2, right? So that means what we need to find is the expected value of B minus 2 square. Okay, which is going to be 1/2, right? Probability of 1 minus 2 square, right? Plus a half times 3 minus 2 square. And that comes out to be a half times what? 1 plus a half times 1, which is 1. Okay, so far so good. So the variance of the random variable B is 1. Everyone good? Any questions so far though? This is like the most basic example. Okay, let me ask you one thing. Let me ask you one very important thing. What's the unit? 1 what? What did we find? We find the variance of B. We find, like we ask on average, what is the distance square from the average? Like, what's the unit? What's the unit? 1 what? 1 baht. Are you sure? Are you sure 1 baht? Not 1 baht. If you think about it, right? If you think about this, it's not 1 baht. It's actually 1 part square, which is why the unit looks funny. It's 1 part square. Because what you're doing here, right? Because think about this. That 1 minus 2 is actually 1 part minus 2 part. So this thing is 1 part. And then you square it. So you get part square. So it's 1 part square. Which is a funny unit, right? Which is a funny unit. Okay? Which is a funny unit. Which is why you also define another thing. Okay, let me define another thing. We also define the standard deviation. You probably have heard about this before. The standard deviation. Okay, we typically call sigma of b, where b is a random variable, is square root of the variance. Okay, that's why we define standard deviation. And this will have the unit of part. The unit will be exactly whatever the unit of b is. Okay, unlike variance, which has the unit of the random variable square, the standard deviation has the unit of the random variable, which is also why you can do the following. Okay, when people draw a distribution, we haven't talked about how to do continuous distribution, which we're not going to do it in this class. So which is why when we talk about continuous distribution, RV is random variable. Okay, RV is random variable. So that is why we can draw something like this, that this thing is like sigma, right? Because you can draw it on the same scale as a random variable. This is like B, that's your sigma. When you see it in statistic, you don't see people draw variance on the graph. You only see people draw standard deviation on the graph because at least it shares the same unit. Okay, so far so good. I will need to teach you a couple things before I can tell you why we bother to calculate it. But it's actually quantify the risk. Okay. Let's get all the mechanics out of the way. So another way we can calculate it, right? You can see that. Let's do another example. To make sure for now, you learn how to calculate variance. Yes. Is this used a lot in quantum? Yes. It's actually Heisenberg uncertainty. Heisenberg uncertainty is exactly what I was talking about. That's the delta p and delta x. This is the guy. This is typically what you call delta p and delta x. Delta p and delta x less than greater than h bar or something. Okay, so let's do this. There is another way to calculate the variance. Okay, so variance, we define it as the following, right? Variance of R is expected value of x minus expected value, oops, not xr, r minus expected value of r, and then the whole thing square. Which, when you read the symbol, it looks so confusing, right? Because it's expected value, and what am I doing, right? Okay, so I claim we can simplify this. Let's simplify it. Okay, you learned it from the brute force way before. You can do this. Brute force way, you can do this. But once you have like 6-sided dice, for example, you don't want to calculate it this way. It's sad. Okay, you could though. Okay, let's simplify this. And the way we simplify it, we're just going to expand it. Okay, we're going to make it look even more terrible. Okay, it's going to be expected value of r squared minus 2 times r expected value of r. And you ask, Ajahn, this look even more complicated than last time. Bear with me. It's going to simplify and looks really nice. Expected value of r squared. R and then square, right? This is the thing inside. When you square it, you get 3 terms, and it looks like this. Okay, and it looks like this. Okay, so far so good. What is so tempting to do when you see this? What's so tempting to do? 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 When you see expected value of three things added together, what should you do? No, 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 no. You separate them. You average. What you do, you use, like I said, if you want to sound smart, say this word: linearity of expectation. You're gonna sound like 25% smarter. That's exactly what we just did. A squared plus 2ab plus b squared. That's exactly what we just did. Okay, so what we're doing now is going to be expected value of r squared, right? We know that from linearity of expectation, minus expected value of 2e of r, right? Plus e of r squared. Oops, 2, sorry about that, r e of r. Let me put the 2. You know by now you can pull the constant out, right? Okay, so far so good? So far so good. These two guys, be careful. These two guys, even though they look the same, they're totally different things. Okay, you square, then take the expected value. The other one, you take the expected value and then you square. We're gonna do example, but just to note to you that these two are totally different things. They are totally different things. Okay, so the next thing that we're gonna do, right? We can kind of see that the left term and the right term, those are friendly, but the middle term is like, come on, Ajahn, guy, what kind of symbol is this? What kind of language is this? Okay, so let me do this. Okay, let me help you. Let me just copy the first and the last term. It actually looks complicated, but it's actually very simple once you understand what's going on inside. Okay, E of R, this thing is a number, right? Expected value of something is clearly a number and is a constant, right? So for example, I asked you, what is expected value of the face of the dice? You tell me 3.5. Let's say you draw a dice. Okay, expected value is 3.5. It doesn't matter what you throw. The expected value is 3.5, right? You could throw this guy and you get 1. And then I ask you, what is the expected value? Say 3.5. You can throw this guy and you can get 2. And then I ask you, what's the expected value? It's still 3.5, which means this guy, oops, which means this guy, expected value of R is like 3.5. It's a number. It doesn't depend on what you roll. What you roll is this guy. Right? Which means you can also pull this guy out because this guy is a number. Think about it as 3.5, right? It serves the same purpose as 2. Yeah, expected value doesn't change. Okay, so this guy becomes 2 times, let me put one in blue and the other one, expected value of R multiplied, and this guy is this one, multiplied by expected value of R. This is whatever left over. Is someone good? This argument is, you can actually check, you can actually prove it, but intuition is exactly what I said. Expected value of the dice is a constant. It doesn't depend on what you roll. Okay. What are we doing here? Because we hope that it's going to simplify. We hope that this guy is going to simplify to something that looks nicer. Someone with me so far though? This is an especially important step because the symbol looks so confusing. Okay. Expected value of the dice is a constant. Okay. Okay. So let's continue. So what cancel out though? Can you tell me what cancel out? Why is the last one? You mean the third one? This one? Because you get it from the quadratic, right? You expand this guy, you get a square plus 2ab, actually minus because it's a minus, plus b square. And this thing is b square. That's still b. Oh, I see. I see what you're talking about. Sorry. I skipped one step. It's expected value of r square. Sorry about that. But the same idea. I asked you what is expected value of d1 square. You tell me, okay, Ajahn, it is, I don't know, let me make out the number though. Don't trust me on it. It's 10. And then I let you toss the dice again. I asked you the expected value, not the value that you get. Then you can tell me 10 again. This is like expected value of 10. Right? So that means you should tell me 10 as the answer. So that's why you only have this guy alone. Okay. That's good. It's the same argument as what I did over here. It's the same argument that expected value of the dice is constant. It doesn't depend on what you roll. Okay. Expected value of the dice is what happened if you roll it infinite time and take the average, not for one particular roll. That's why you can throw. That's why you can put it out. Okay, but I didn't write it like 10. But when you see 10, you know you can do that right away. Okay, so you're gonna notice that a whole bunch of things cancel, like this guy and that guy sort of subtract each other, right? So what you're gonna be left with is e of r square minus e of r and then square. You may think it's zero. No, they are not zero. Like I said, that this guy you square it first and then find expected value, and this guy you find the expected value first, then square. Okay, so let's do some example. So you're gonna see how painful this guy is. Okay. Okay. So let's do something really painful, like expected value, the variance. So D1 is a dice. Yes. Let us do the example so you know how to calculate this. Let's just do the example. So let's say we want to calculate the variance of the face of the dice. Okay, dice face. Okay, and it's a fair dice and everything as well. Okay, so what we can do, right? We know that the variance, there are two ways to calculate it, right? There is d minus e of d, and then the whole thing square, which we know is also equal to e of d square minus e of d square. Which one looks simpler though? I just asked you for your opinion, left or right? They are equivalent, right? We show that they have to be equal. Which one looks easier if you want to calculate? The right one looks easier. Like it even have less symbol, right? It even have less symbol. Okay, so let's do this. Let's calculate it using the right one. Let's calculate it using the right one. Okay. Okay, so that means I need to find two things. I need to find e of d square. That's the first term, right? That's the first term. And the second term, I need to find e of d. Right? I have to find e of d, which we know by now, right? 3.5. You tell me so many times today already. It's 3.5. Okay. Now, e of d square, you may think, Ajahn, this is easy. You just learn it, right? Ajahn, this thing is e of d times d, right? And then that means it's also e of d times e of d. So that means, Ajahn, that's 3.5 squared. So that means the variance of this thing is 0. Is that correct though? What did I do wrong? That doesn't sound right, right? Too good to be true. Yes. What did I do wrong though? What did I do wrong? What did I do wrong? What's wrong with this? What's wrong with this argument? What do we need here? We need D and D to be independent, but D and D is like the exact opposite of being independent, right? Because if you know D, you know D by definition. They are not independent, so this is not true. So yes, your dream is lost. Okay, is everyone good? They are not independent. That they are the opposite of independent. They are exactly the same thing. So no, you cannot do this. So no, you cannot do this. You just need to go back and do it brute force way. So that means it's gonna be 1/6 times 1 square plus 1/6 times 2 square plus 1/6 times 3 square plus 1/6 times 4 square plus 1/6 times 5 square plus 1/6 times 6 square. Typically, things like this, you let computer do it. But I am so nice. I did it for you already. It's 15 1/6 because we just did that. Okay, so far so good. So far so good. Okay, which means that means the variance of D now it's become much easier, right? The variance of D is going to be 15 1/6 minus 3.5 square. Notice though, I want to point out these two guys are totally different things, right? Are we good? Are we good? Saran, that you asked me about the position of square before. This is the difference. Okay. You square first, then find the average. The other one, you find the average, then square. Anyone else? Any questions? So any questions? So then you get some number. I don't know what that number is. Okay. But it's guaranteed to be positive. How do we know it's positive though? Anyone knows that? I know for a fact that it has to be a positive number. Let me move from alpha for a second. How do I know it's a positive one? 15 is greater than 3 squared, but that's a 0.5, right? 15 plus 1/6 minus 3.5. Well, my point is not that big. Not bad. This thing is about 2.9. 2.92. Okay, and the square root of this guy is it's about 1.7. Okay, the reason that I know it's positive because I know that this guy, if you look at it, oh, Ajahn, this thing could be positive or negative. Yeah, I kind of agree, right? It's not so obvious that this guy has to be positive. But if you look at this guy, it's the expected value of something that is always positive or maybe non-negative. Let's call it non-negative, right? Expected value of something non-negative. It should come out to be something non-negative, right? You take the mean of all the things that are not negative. The mean should be either 0, if in a very special case, or some positive number. Are we good? That's good. Any questions so far? Though? Any questions so far? I know this has to be positive because of this guy, right? It's the same thing. My expected value of something that is always non-negative should be non-negative. Any questions so far? You can calculate it using the left one as well, but it's kind of a pain. Let me write it, but we're not going to calculate it. Let me write it. If you use the left one, guess what's going to be what happened? You're going to need to do 1/6, right? Times 1 minus 3.5 square plus 1/6 times 2 minus 3.5 and then square plus 1/6, 3 minus 3.5 and then square plus dot 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 plus 1/6 times 6 minus 3.5 and then square. That's what you need to do if you do this one. Okay. If you look at it, it's kind of a pain. Any questions so far though? Any questions so far? You can calculate the variance either way you like, but I kind of prefer the right. The right one is actually easier to write in Python. It's not faster though, but it's easier to write. Okay, any other question though? Any other question? Okay, if no question, let me ask you one thing. We learned, right? We learned this formula. We learned this guy. When is it that the variance is 0? Okay, let me ask you. The variance of D is this guy. I asked you, what kind of situation gonna give you 0 for the variance? What kind of situation? We know it's gonna be non-negative for sure. But I asked you, how do you get it to be 0? Both are 0? That's one way. Can you make something more generic though? How do we make it 0? Right? Think about your example, right? Think about your example. Okay. So if you want to make this guy 0, right? Good. If you want to make this guy 0, right? That's the only way for you to make the variance 0. You need to make this 0 for every single term that D has, right? So that means you want D to give you the mean every time. So D is expected value of D every time. That means your answer would be whatever you do, you're gonna get exactly the same number. That's how you get the variance to be 0. And we get the variance of a constant is 0. Right? Because it never varies by the name. You even look at the name. Variance is like how much it varies, right? Variance typically means how much it varies. How much does constant vary? 0. Good, because you never get anything. You never get anything beyond the mean. You always get the mean because it's a constant. Okay. So let me look at this. What else do I need to teach you? Blah, blah, blah. Do I have the time? Yes, I do. Okay. So let's look at this. Okay. So if you look at this, the variance of, I don't know, x plus 5. Okay. So remember, variance is how much it moves around the means, right? So you take the mean, right? And then you ask how much it moves around, how much your answer moves around the mean. Okay. Here's what we are doing. We are taking the variance of some random variable that we shifted by 5. So the mean was here. And then I copy this guy, and then I'm going to paste it. Paste, and then to the right. So this guy is going to be x, and this is x plus 5. Actually, it moved to the left, but you get the idea. Actually, it's moved to the right. Yes, I'm correct already. Okay, and then I asked you to compare the variance of the two. How much it moves around the mean. What would you tell me though? We haven't proved it yet, but we're gonna prove it. But I want you to see the intuition rather than the formula. You move the graph to the right, and then you ask how much it's moved around the mean, which is essentially the width. What happened to the width? What happens to the width? It stays the same. Variance of x plus 5 is exactly the same thing as the variance of x. Okay. If you shift the mean, it doesn't do anything to the variance. Are we good? Okay. Everyone good, right? So let's do this. Let's actually prove it. Let's actually prove it. Your intuition is correct that if you try to move the graph to the right, nothing happened to the width. Okay. So let's calculate this. Variance of r of x, right? I use x plus 5. Okay. We're gonna come back. I think I'm gonna leave one thing last time. Yes, because every random variable gets +5, and then you ask how much it moves around the mean, because the mean get moves +5 as well, right? The mean gets moved +5, and every random variable get moved +5, and then so that means the distance from it to the mean are the same every time you calculate, right? So that means you get the same variance. So the variance of x plus 5 is going to be, let's do the definition, right? Expected value of x plus 5 minus expected value of x plus 5 and then square, right? This is by the definition. Okay. Okay, I'm gonna leave it right up. Okay, I'm gonna end the class right after this one. Otherwise, it's gonna be this two disconnected. Okay. So the variance of VAR. Okay. So this guy, how do I simplify this? Can anyone help me? Anyone help me? How do I simplify this? Expected value of x plus 5. What do we know about it? How do I simplify that term? Pool the 5. What do you mean by pool the 5? It's not multiplied by 5 though. Right. So it's expected value. It's linearity of expectation, right? Expected value of 5. Okay, I can do like that. What is expected value of 5? If there's a dice that you throw and you get 5 every time, what's the mean? It's exactly 5, right? If there's no, if there's a dice that's so cheated that no matter how you throw, you're gonna get 5 every time. And then they ask, what's the mean of that dice? Then you're gonna say 5, right? So this is 5, yes. And then all these cancel, right? Okay, let me put in the parentheses, right? This and that cancel. And then you're gonna get exactly that E of x minus E of x, and then square. Does this guy look familiar? Yes, it is just the variance of x, and we have just proved that, right? But the intuition is exactly what, like I tell you, that you shift the graph, you did not do anything to the mean. Okay, next time going to be even more magic. Next time even going to be even more magic. Okay, any question? Okay, if not, we're gonna end the class here, and then we're gonna continue on it tomorrow. Okay, see you next time. Okay, bye. I need to call someone.